Okay. Here we go, Ahmad. I think I'm going to try to get through questions 8 through 11 here, and we're definitely getting into some heavy calculus now. So here we go. Just move this out of the way here. Okay. So what's the derivative of 1 over root ln x? So tricky question, but also pretty straightforward because it's just grind out a derivative, and it looks like it has to be simplified to a certain degree. So a couple of ways you can go about it. You can use the quotient rule, which sometimes I try to lean away from when I can, since I can use the chain rule, especially when it's something quick like this. It's just 1 over the root of the or 1 over the denominator. When it's 1 over, it's easy to convert this back into just something to a negative exponent. So that's what I'm going to do here. I'm going to call this y, for the function, and I'm going to rename it as root. Not rename it, but express it as root ln x to -1. Okay, so 1 over anything can be expressed as whatever it is to the power of -1. So, for example, if I had 1 over 10, this is equivalent to 10 to the -1. Same thing. Okay. So now another thing I can do is I've got root ln x. So root I can kind of also express as an exponent. I know that the radical is equal to ln x to the power of 1/2. I'm going to put square brackets because I still got that -1 sticking out there. Okay, so now I've got ln x to the power of 1/2 to the power of -1, and now I've got a power on a power. So using my power rules, I'm going to write that as, multiply those two things together, ln x to the power of -1/2. There we go. Okay, put brackets around there so we can see everything, hopefully. So now I think I can take this derivative, because now it's just a chain rule that's going to be carried out. So here we go. Y prime, or dy by dx, is equal to -1/2 ln x. Subtract 1 from that using my power rule, so -3 over 2. Now take the derivative of the inside. Well, the derivative of ln x is easy. 1 over x. Okay? Now it's just a matter of trying to simplify this to a certain degree. But I can already tell, which one is it going to be? I can already tell that the answer's got to be negative. Like, the answer's going to be negative. When I look at these answers, only D and E are negative. Right? They have a negative sign in them. So I can immediately tell, boom, 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 those aren't right. Okay, both of them have an x in the denominator, and both of them have a 2 in the denominator, which kind of gels with this. So I'm going to do a little bit of work here, but let's see what I got. Ln x to the power of -3/2. So that means I'm going to change this into a rational expression, -1 all over the 2 and the x go in the denominator. They already were denominators. Now this ln x, since it was to the power of negative, and just like we went over here, can be dropped into the denominator. So it'll be ln x to the power of 3/2. Now I'm going really slow here, so I don't skip any steps here. So, but you might kind of get this a little quicker. And if I'm going too slow, then maybe just fast forward. So now the other thing is, I remember how we talked about the radical sign is the same as a 1/2, so I'm going to do this. This is the same as having ln x, or root ln x, excuse me, okay, because of the 1/2, that denominator, 3 times. So 3 of them. So times root ln x times root ln x, right? So 1/2 makes it radicals, and I've got 3 of them. Okay. Now a root times a root, just like if I had, say, for example, root 10 times root 10, well, that's the same as just equal to 10. Okay. So this is equal to 1 over, don't forget the negative, 2x ln x times root ln x. And there we have it. Those two, the radicals, multiplied by each other, and just kind of a 1/2 plus a 1/2 is 1. That's why it becomes just ln x. So there's my answer. And which one is it? Right there. Okay? It's that one. So it's D. Okay, tricky question, especially because of the simplifying. Like the derivative actually isn't too bad, a chain rule, and you're understanding that the derivative of ln x equals to 1 over x. But the simplifying, a little bit of algebra. Okay. All right. Here we go. This one again. These are getting tougher. G of x is concave up if and only if. Which one of these conditions is true for that function? So when we say concavity, we're thinking about second derivative. So we want to know when is the second derivative going to be equal to 0, because those are more than likely points of inflection. And we want to know for concave up, when is that second derivative going to be greater than 0. So I first got to grind out my derivatives. So g prime x. Now this is going to require product rule. Okay, so f prime g, so the derivative first, well, derivative of x is just 1 g, so f prime g. Don't forget the product rule is f prime g plus g primed f, or your prof may have written it slightly differently. Some of them use u prime v plus v primed u, but there we have it. So f prime, the derivative of x is 1 g e to the negative x, plus g prime, well, that means the derivative of e to the negative x, which is e to negative x. Don't forget to take the derivative of the exponent, which in this case is negative 1. So there's my g primed times f, which is x. Okay, I'm going to clean this up a little bit because of all the brackets and stuff. So I'm going to write e to negative x, negative, I'm going to kind of bring that up front here, and x e to negative x. Okay, I can factor the e to the negative x and all that, but I'm just going to leave it alone because I've got to get the second derivative too. So here we go. G primed, but now g double prime, the second derivative. E to the negative x, well, we've done that already. It's e to negative x again times negative 1. Okay, and then the derivative of, I can do this separately, but you got to be careful with this negative sign. So I'm going to use that as a negative x. If you did it separately, like if you just took the derivative of this, which is actually the original function, you'd have to distribute that negative through at the end. So you got to be careful. So I'm just actually going to consider that altogether negative x. So here we go. Another product rule. So f primed, which will be negative 1, g e to negative x. I could have just wrote negative, but that's okay. I just want to make sure you see that I took the derivative of f prime. There we go. So f prime g plus g primed f plus, again, there's my e to negative x again, e to negative x times negative 1 times negative x. Okay, so g primed f. Okay, so now here we go, a little bit of cleaning up to do. Negative e to negative x, okay. Here, that's still another negative e to negative x. Then just clean this up a bit. The negative 1 times the negative x is just x, so plus x e to negative x. So I want to know when this is greater than 0, right? Okay. So, but I still can do a little bit of algebra. These are actually the exact same terms. So negative 1 of them, take away another one, is negative 2 of them. Okay, I'm finally ready to try to figure out when it's concave up, because I want to know when is g double primed x greater than 0. So that's when concave up. Okay, that's when it's concave up. Okay, so I'm going to take this expression over here, negative 2 e to negative x, okay, plus x e negative x. I want to know when is that positive, when is it greater than 0. Okay, notice that e to negative x is common to both terms, so I'm going to factor that out, e to negative x, and I'm left with negative 2 from the first term, right, because that's been factored out. From the second term, just left with plus x. It's greater than 0. So I've got a product of two things, and they're ending up with that it's greater than 0. Well, this term here, e to negative x, is always positive, okay? E to whatever it is, 3x, whatever it might be, is always positive, okay? So this, and I think that came up earlier, this is always positive. You can stick whatever you want in for x, you're never going to get e to the negative whatever being a negative answer. So this is always positive. So for the overall expression to be greater than 0, then that means that this must also be positive somehow. Okay? If this is negative, then I've got a positive times a negative. That's no good. Okay? I want to know, when is negative 2 plus x going to be greater than 0? Okay? Well, just bring that over to the other side. So I got negative 2 plus x, x plus 2, and so I'm going to add 2 to both sides. I'm just going to write that. X will be greater than 2. So it will be concave up if and only if x is greater than 2, which is in this case is A. Tough question, okay? But if you take your time with it, okay? And again, there's a lot of stuff you got to kind of use. Your understanding of the product rule, your understanding of the derivative of e to the negative x, and there's a chain in there. But it's really getting at your understanding of concavity, knowing that this means the second derivative is greater than 0. And once you finally get to there, is understanding how to solve that inequality. Okay? All right, let's move on to question number 10. Okay. Let's see if I can switch to a marker here. I think I had a marker. Did I marker? Oh, okay. Okay, I've got a marker here. It might be a little darker. I was noticing that was a little faint there. Okay, I just got to make sure I don't make mistakes on this now. Okay, with this one was actually a little easier. It's asking you to find the equation of the tangent to the curve y equals f of x at x equals 1, and so there's our function. So when we're finding the equation of a tangent, we need to know the slope at the point, and we need to know what the point is. We need to know the point. Okay, so we need to have those two things. Okay, to get the slope at a point, we're going to have to take the derivative of the function and plug in the x value, so that'll take care of that. And to get the point, if we don't have it, well, then you got to plug this into the original function to find the y value to it. So that's right. A point is an x and a y coordinate. So we've got to take this x and plug it into the original function to find the y. And now we'll have the point. And then again, to find the slope, we've got to take the derivative of that function, over here, and plug in x equals 1. Okay, so here we go. So why don't I handle the easy part first, which is taking care of the point. So I'm going to find out what is the value of the function at 1. So I got e, so I'm going to replace x with 1, minus ln 1. Okay. E to the power 1, well, I'm not going to mess around with decimals. I'll just say that's equal to e. Now this is good. Ln 1, what is that equal to? So remember, ln, the answer to the logarithm is an exponent. So in this case, ln has a base of e. So we're asking, or you should be thinking, what is the exponent I got to put on e to get an answer of 1? So e to what exponent equals 1? Which in this case, and in every case actually, is equal to 0. The logarithm of any base, and if you're trying to figure out 1 is equal to 1, is always 0, because anything to the power of 0 is 1. Okay, so if this had been log of say 13, and 1 is log 1 base 13, what is the exponent? It's 0. Okay, so it doesn't matter what this base is. Okay, if I'm trying to figure out log of 1 to whatever base, the answer is 0. Okay, so that means the answer to f of 1 is just e. Okay, so there it is. So I've got my point, and I'll just maybe write it over here. It's 1, comma, e. So next part, I need to figure out the slope at the point. Well, slope means derivative, so I'm going to find f prime. F primed x is equal to e to the x, right? Derivative of e to the x is just e to the x, and there's no chain needed here, or since it's just x up there. And even if I did chain, derivative of x is 1, so nothing matters. The derivative of ln x, of course, is 1 over x. Okay, so there's my derivative, nice and easy. Now I've got to find the derivative at 1, because that'll be the slope at the point. So what do we got? E to the power of 1 minus 1 over 1, which is just 1, which equals e to the minus 1. So now I've got my slope, and I've got my point. It's time to find the equation line. So I like to use this form of the equation to find the equation line. I'm not too sure what you use, but I just use this all the time, especially in more advanced math classes, because kids should understand this. So y minus y1 equals the slope times x minus x1. It's actually the slope formula. Okay? It's actually the slope formula. Okay? But I've just rearranged it. Okay? So I've multiplied both sides by x2 minus x1, so that goes over here. Okay? And so, but this time I'm not plugging in numbers for y and x, I'm plugging in numbers for just y1 and x1. I'm plugging in my point. Okay? So here we go. Y minus y1, so this is the y value from my point. Okay? Because remember, slope is this. Okay? Y minus y1, well, y1 was e. So y minus e equals the slope, which is e minus 1. I'm going to put that in brackets because that's two terms. Okay, make sure there. Times x minus the x coordinate of my point, which is 1. Okay, almost done. I'm going to isolate for y because it looks like all the answers are in y equals form. So y equals, I might try to clean this up a little bit. I might try to clean this up a little bit. Bring that e x minus 1 times plus e. There we have it. Okay. So now I've got to kind of figure out which one works, which one is the correct answer. So I'm going to multiply this through. It's a little messy, but that's okay. So I'm going to expand this quickly. So e times x minus e minus x plus 1 plus e. So I expanded. Those two brackets got this. Collect some like terms. Maybe clean this up a bit. Minus e plus e. Hey, that's 0. That's nice. So I'm left with ex minus x plus 1. Almost done. Ex minus x plus 1. Factor out x from those first two terms. I'm left with this. Okay, x times e minus 1 plus 1, which is, if you look at it, right there. It's d. Okay. All right. Let's finish up with number 11 here, and then I'll post this one. Okay, suppose that a person's performance in an agility test is this, where t is measured in years. At what age t, so we're going to be solving for t, is the person at their highest, and that's a key word, highest level of performance. So highest implies maximum, and so when we find the maximum or the minimum of a function, we're optimizing it, which means we're finding when is the first derivative going to be equal 0, because maximum or minimum values occur at critical points, and critical points are determined by finding when is the derivative equal to 0. So I've got to find the derivative of this and figure out when is it equal to 0. Now this is a nasty one because it's got a product rule and a chain rule, so it's a tough one. And then we've got a little bit of algebra. So here we go. P prime t is equal to, so my f primes, my f here is 1/8 t, and my g is e to the negative 0.05 t. So the derivative of 1/8 t will just be 1/8. Okay, so the derivative with respect to t times e to the negative 0.05 t. Okay, so that's f prime g. Now g primed f, here we go, plus e to negative 0.05 t, so the derivative of e to that is the same thing. Don't forget there is a chain here though. Derivative of the exponent is just negative 0.05. So there's my g primed f times 1/8 t. Woo, that's nasty. So now I know, just looking at the answers and solving this, I'm going to change this negative 0.05 into a fraction, because eventually I'm pretty sure that this is going to need to be when I solve it, but let's continue on. Can't do much here, so I'll just leave that alone for a second. A little cleanup here. So as I said, I can change this into a fraction. Maybe I'll just do this on the side. That's 5 over 100. Okay, so that's 5 over 100, which reduces to 1/20. So this is the same as negative 1/20. Okay, negative 1/20, and it's going to be multiplying by 1/8. So negative 1/20. Okay, that's the equivalent to negative 0.05. It's going to be multiplying by 1/8, which is equal to 1 over 160, or negative 1 over 160. So just trying to do a little bit quickly there. Okay, so that all together here is negative 1 over 160 t. times e to the negative 0.05t. All right, now we want to know when is this going to equal 0. So I'm just going to stick a 0 here. Okay, I want to know when is this going to equal 0. So time to get at it. So I'm going to factor out a 1/8. Okay, 1/8 can be factored out of each one. In fact, you could have seen that from here. Notice that 1/8 is common to both terms. Okay, I'm going to factor out 1/8 and e to negative 0.05t, which is also common. So here we go. This is actually close to the end. So 1/8 e negative 0.05t. Okay, now what am I left with? Well, from the first term, nothing really, right? It's all been factored out, so that's 1. Okay, it shouldn't say nothing. It's not like it's 0. It's just been divided itself away. Remember, that's what factoring is, dividing out. So I've divided everything out of the first term, so I'm just left with 1. Now, 1/8 divided by 1/60, well, that's this again. That's that 1/20th, because that's how we got 1 over 160. We multiplied 1/8 times 1/20th. So if I'm taking out 1/8, I must have the 1/20th left. So 1/20th. And then I factored out this, so I'm just left with t. Okay, so when is this going to equal 0? Well, this can never equal 0. Okay, e to negative 0.05 to the exponent t. E to the exponent negative 0.05t is never. This can never equal 0. Okay. Okay. You can check it if you like. If you want to try some number that will make e to whatever it is equal 0, it's impossible. You'll be there forever. Okay. There's no possible value for t that will make e to it equal 0. It's always positive. Okay. So that means that the only way that the p prime t is equal to 0 is if somehow this part of the derivative equals 0. So let's take that and set it equal to 0 and solve it. So I'll bring the 1 over. Okay, multiply both sides by negative 20 to get rid of that. And I'm left with, well, that divides everything away here. I'm left with t equals 20. There it is. So what's the answer? Right here. So it takes 20 years for a person to reach their highest level of performance. Okay. Tough question. Again, the derivative was tough because of the product rule. It's testing your understanding of the product rule, but it's also testing your understanding that to find the optimal value for a function, that you have to find the critical points by setting the derivative equal to 0 and solving. Okay, so optimal values are found at critical points, which is where the derivative is equal to 0. Okay, so I'm going to post this one now and hopefully finish it up soon.